All right, I'll get started. Hi, my name is Eddie Kim. I'm a postdoc in advised by Sanjit. Let me just go straight into use of VerifAI with Scenic. Okay. All right, so let me start off with why do we need VerifAI in the first place? Is that the okay? So first, Scenic program is actually intended, as you saw yesterday, Scenic is intended to model environments and generate modeling and generating environments in simulation. And there can be different usage, but let's say if it's like testing, for example, in terms of if we want to test, what are the basic ingredients? We want to specify the metrics, the specification that we want to test the systems with respect to, right? So that specification aspect. And also another aspect is that Scenic program itself contains distribution of environment. So another question is, in addition to the specification, how do we explore this distribution? More technically, how do we sample through this distribution that is defined in the Scenic program in order to, for example, the use case is testing, in order to identify as many test cases as possible. But at the same time, in addition to that, if you want to, as you're sampling and searching for failure cases, the scenarios in which your system fails, you want to also find as diverse test cases, as diverse scenarios in which your system fails. You don't want to find just small variations of the same environment, but ideally you want to also be able to find diverse type of situations. So there's a trade-off here, right? So not just finding many failure scenarios is not the objective. You want to find as many, but at the same time, you want to also find diverse failure scenarios. So there's a trade-off here. You want to explore as much as you can in that distribution, but at the same time, you want to exploit, and also exploit meaning once you find certain failure scenario, you want to also exploit around that region of area where the variations of that scenario to also see how your system is failing. So that's where VerifAI comes in. Scenic is purely for modeling the environment. Now, in terms of specifying the properties with which you want to test your system with, and also in terms of exploring sampling through the distributions modeled in the Scenic program, that's where VerifAI comes in. So here is a architecture of VerifAI. So first, you put 3 inputs. So first is the system. What is the system that you're testing? So this could be a component, or it could be an end-to-end. So for example, from JICE, it could be the auto-aware that you're testing, or it could be perception model or behavior prediction model, the components that you're testing. And then the environment is we're modeling in terms of Scenic program. And then the last is a specification. And given this, VerifAI, in particular, given the Scenic program, it internally parses out all the semantic distributions over the semantic feature space. So it could be over the positions, distance, whatever distribution that you specified in the Scenic program. And then now that we formally extract out that distribution space, now within VerifAI, it starts to sample within that semantic feature space, which is modeling the distributions. And there are different types of search strategies that can be employed. For example, right now we're supporting Bayesian optimization, multi-arm bandit, cross entropy, simulated annealing, Haughton random. there are different types of samplers that we already support in VerifAI. However, you can also add your own samplers too. And we have a pipeline system in place such that you can do more intelligent sampling by accounting for the history of when your system failed. In particular, this arrow that you see between the monitor and the search, that is providing you the history. So you sample an environment using the sampler here in this search, and then that sampled environment is sent to the simulator to be generated. And then in that simulator, the system that you're testing is running, let's say the autopilot. And then the outcome after each simulation ends, that outcome is monitored here. So for example, we're collecting all the trajectories of the objects, including the system that is being under test, as well as the environment agents. And then let's say, for example, the specification was safety distance of 5 meters must be enforced at all times. So during this monitoring phase, using the specification that you provided, we compute whether that specification has been violated or not, and that result is inputted back to the sampler to inform the history of how your system is performing depending on which sampled environments. And also the monitored result, you can also save it as like a CSV file, so that you can also do further analysis afterwards. And right now within VerifAI, we also provide some support to do this error analysis by using, for example, k-means clustering, so that you can try to cluster the semantic features that are responsible, that is highly correlated to the failures of your system over the particular range of semantic feature values and so on. Yeah. Any questions so far?
Are you going to cover for people how they can add samplers?
No, not here. But I just wanted to let you know that you could potentially do that. In fact, I think we should update our documentation.
VerifAI documentation is not as comprehensive, shall we say, as the Scenic documentation, although we are working on it. But there is a way to essentially, I think with not too much pain, add your own sampler and add as an option in VerifAI. So I think we're happy to work with people during the hands-on session. Yeah, if you're interested in that.
Yeah, and also for those who are attending, let me share some secret. As in, we're preparing to submit a follow-up tool paper to another conference in October, and in that process, we're planning to update our documentation as to how to add your own samplers easily and so on. And so we're open to helping people out directly so that we can also create our documentation, share it with you, and then refine it with you. And so you can be the first beneficiary of this effort in the process. So just let us know if you want to add your own samplers. All right. And then there can be many use cases for VerifAI, right? Starting from fuzz testing, falsification, failure analysis, data augmentation or retraining. And then the last one is parameter synthesis for the controller that you have, template-based controllers and so on. Okay, so how does it look like? Hopefully you can see. So for example, let's say you have your own perception model that you want to test. So that is your system. And you want to test that system using Scenic and VerifAI. So first of all, if you're using PyTorch, the upper pink box that you see, it's importing the PyTorch, and you can load, for example, the perception model that you want to test, and then specify, for example, the attributes of the image size or sensor data that you want to collect. And then below, as Daniel covered yesterday, using Scenic program, programmatically, you can specify what kind of synthetic sensor data that you want, not synthetic, what kind of data that you want to collect using Scenic, right? So below your recording, we're recording in line 24 and 25. So right above the pink box below, we're recording the semantic segmentation labels as data, as well as front RGB camera data.
It's hard to beat that, then you can look here. Slightly better.
Yeah, we'll share this with you, but just know that you can do this. You can specify programmatically inside the Scenic program as to what type of sensor data that you want to collect. And then all the way inside the pink box below, we're specifying that using the ML model that you imported above, now inside you're also recording the outcome of your ML model. So I guess you can't see this, but inside the pink box below, you're inputting the front RGB sensor data as well as front segmentation sensor data. And then you're collecting that output of the ML model during simulation. And then once you collect those data, now this is so what I just showed you was a Scenic program, modeling the environment, specifying what data to collect, importing the system that you want to test, and then feeding in the sensor data to that system, the perception model, and then also recording the outcome, the output of that perception model too. And now moving on to the VerifAI side, this is a Python script where you're specifying the specification input as well, specification. Yeah. So here, in the Scenic program, we're recording with a keyword ML performance. So here, you just have to follow some templatized program that we provide you. But here, you can assume that the simulation results is including the data that you're looking for. So right now in the previously, below we're collecting the output of the perception model as ML model output here. Sorry if you can't see it. And then here, I'm calling that again. So sorry, it should be ML model output model here, but it has ML performance. So it should be ML model output, and then you can get the output of your perception model's output, and then analyze that, in this case, using, let's say, a popular metric in perception, for example, IOU. And then output that IOU. So each time you run a simulation, we're collecting the data, in this case, the output of the perception model, at every time step throughout that simulation. And then here we're accessing that information in this line 6 and 7, and then computing a particular metric outcome, which is using IOU, mean IOU. And then here from line 12 to 19, you're specifying different configuration that you want to run the test with. So here, line 14, we're specifying the number of simulations that you want to run. So here I'm specifying as run 1,000 simulation using that Scenic program. So it will sample 1,000 times from that distribution of Scenic program that you specified. And for each simulation, what is the maximum amount of time that you want to run for? I said 20 seconds. What is a falsification threshold? Meaning, okay, if the mean, what is the threshold to determine whether that mean IOU was good or not? So if you want to convert that into Boolean here. So if it's less than 0.5, if the mean IOU is less than 0.5, now we consider that as a failure. And remember, in VerifAI, after each simulation, you monitor the outcome and then feed that outcome back to your sampler, right? So this is a part where that's being computed. And you can also specify, okay, do I want to save all the errors that have been found? You can specify yes, true over here in 17. In line 18, you can also specify whether I want to also save all the environments in which my system performed correctly as well. Yeah, any questions so far? Okay. So the demo here is a badly parked car case. And that right now the specification is that the safety distance between the Eagle car, which is the car right in front, and the badly parked car, which is going to pull in as the Eagle car approaches, that safety distance has to be greater than a certain number. I believe it was 5 meters in this case. So let's see if that's enforced all the time. So this time, I think here we're going to run it for 3 or 5 simulations. And then each time simulation ends, it will compute the outcome, monitor the specification result. So right now, oops, yeah, let me just show you. So here it's outputting, in this case, in all 3 simulations, the distance between the two was actually greater than 5 meters. So I'm not sure whether you can see, but it's outputting a safe table there as a CSV file. And later down, I'm importing the CSV file. And here I see each column is representing different semantic feature value that was sampled. So object position, object color, RGB color. So what was the value of RGB from 0 to 255 value? What was the model of the color that was selected? What was the time of day? What was the weather condition for that scenario? And so on. Yeah. So the environment semantic feature values. Okay. So that's it. And then let me have Kai-Chun continue here, and then we can come back and have a hands-on session using VerifAI.
So can you ask Kai-Chun to unmute himself, share?
Kai-Chun, are you there? Kai-Chun, can you hear me?
Yeah.
Kai-Chun, can you hear me?
Yeah.
Okay. Would you share your screen?
Yeah. Yeah, just 1 second. Okay. Yeah. Could you see my slides?
Yes, go ahead, please.
Okay, thank you. Okay, so hello, I'm Kai-Chun from UC Berkeley. I'm a PhD student advised by Sanjit. So I'm going to present our work on Scenic plus rulebook. It is a benchmark for multi-objective autonomous driving scenarios. And this is an ongoing work, so we are opening to any suggestions. So in modern traffic environments, multiple objectives exist at the same time. So for example, for an autonomous driving vehicle, it has to avoid collisions, maintain clearance with other objects, obey traffic rules, ensure passenger comfort, and make progress toward the destination. So all of these objectives exist at the same time, and moreover, there are priority relations among these objectives. So for example, in most of the time, we would prioritize avoiding collisions over, for example, ensure passenger comfort. So to develop our autonomous driving algorithms, we need to develop a benchmark that consider all of these objectives and their priority relations. So in this work, we first collect and formalize a set of generic traffic rules for autonomous driving. And then we design a reference priority structure for autonomous driving scenarios that provide generic priority relations of all these rules. And then we develop a benchmark of scenarios with multi-objective specifications. So these are the rules we collect from the literature. There are 23 traffic rules in total, from no collisions with pedestrians or vehicles, and some precautionary rules such as time to collision, VRU acknowledgement, and we also have some clearance rules, yielding rules, and some traffic rules such as speed limit, turn signal, lane keeping. And then we have this go progress rules, which means the ego vehicle need to map progress or reach the target region. And we also have some passenger comfort rules. And then we use signal temporal logic to formally define these rules. So signal temporal logic is an extension of linear temporal logic with real-time, real-value constraints. And an advantage of signal temporal logic is that it can naturally capture the degree of violation to a rule. So for example, one of the rule is staying within the drivable area. So in Scenic, we can represent a vehicle object as a polygon. So this P0T, is the polygon of the ego vehicle at time t. And similarly, we can use polygon or multi-polygon to denote the drivable region of in the simulation environment. So this is the drivable area. And then we can check if the polygon of the ego vehicle is within the drivable area. So if this phi1 holds all the time during the simulation time interval, then we say this staying with the drivable area rule is satisfied. Otherwise, it's violated. And the degree of violation can be, for example, defined as how long the ego vehicle is outside the drivable area during the simulation time interval. So after we define these rules, we want to specify multiple rules simultaneously. So we adopt rulebook. Rulebook is a specification structure supporting multiple objectives with relative priorities. So for example, this and rulebook is is a tuple of a set of rules and a partial order on this set of rules, indicating the relative priority. And it can be represented as a directed graph. So for example, this rulebook consists of 6 rules, R1 to R6, and we use this edge to denote that, for example, R1 is of a higher priority than R2. So R1 is higher than R2, and R2 is higher than R3 and R4. But for example, R3 and R4 are incomparable in this case. So rulebook supports a partial order. So you don't need to specify all the priority relation among all the pairs of rules. You can also have this kind of incomparable rules. So it's a very highly flexible specification structure. So using rulebook, we design a reference priority structure of rules. Due to time limitation, let me just skip the detail of this priority structure. But basically we the highest level is safety critical rules. So for example, no collisions with VRU or vehicles. And then we have some safety related rules such as precautionary measures, operational limits, and also some safety enhancing rules. And then we have regularity compliance rules such as speed limits and turn signals, and some other predictability rules such as lane keeping, lane centering, maintaining a safe following distance. And we also have progress rules and passenger comfort rules. So note that this priority structure is just a reference structure for users of this benchmark, but users can still modify this reference structure or use their own priority structure during evaluation. And then in our benchmark, we collect several scenarios and specification pairs. So basically, scenario could be represented as a Scenic program, and specification can be captured using rulebook structure. So we are still collecting this scenario and specification pairs, but basically this is how our benchmark will look like. And let me show some preliminary results of this benchmark. So we evaluate our collected rules and our reference rulebook against human annotations. So we use the reasonable crowd dataset, which is a dataset includes over 500 vehicle trajectories across 92 scenarios. And each of the for each pair of the trajectories, they are annotated with human preferences. So for example, in this scenario, U2, there are several vehicle trajectories, U2A to U2H. So for each possible pair of trajectories, for example, U2A and U2B, these are the human annotators that agree U2A is a better trajectory than U2B. So using this data set, we evaluate the degree of violation with respect to our proposed reference rulebook. And then for each pair of trajectory, we compare our rulebook preference against the human preferences. And the current agreement rate of our rulebook preference against the human annotations is around 70%. And we believe after some like fine-tuning of the parameters or some further refinement of our rulebook, we can further increase its accuracy. Yeah, so this concludes my presentation. Thank you.